The epsilon NTU method for heat exchanger analysis is very useful when the inlet temperatures are known and the heat exchanger parameters are known, but the outlet temperatures are not known. There are interesting issues that occur when we have what is called a balanced flow heat exchanger. A balanced flow heat exchanger is a heat exchanger that has a capacity ratio equal to 1. So the capacity ratio, RC, is defined as the minimum heat capacity value divided by the max heat capacity value. Remember that C is given as the mass flow rate times the heat capacity. When we have a balanced system and the cold stream capacity is the same as the hot stream capacity, RC is 1. When we talk about a parallel flow system, this gives a relatively simple limit. So a simple two-system parallel flow heat exchanger, the heat exchanger effectiveness is given in terms of NTU and the capacity ratio. Allowing the capacity ratio to be equal to 1, we see the denominator is equal to 2, and we see that the argument of the exponential is minus 2 times NTU. So it's 1/2, 1 minus exponential of minus 2 times NTU. For the counterflow heat exchanger, it's a little bit more complicated. So for the counterflow heat exchanger, we see that when the capacity ratio is equal to 1, the argument of the exponential is equal to 0 in both the numerator and the denominator. And so for the numerator, we have 1 minus e to the minus 0, or 1 minus e to the 0, which is 1 minus 1, which is equal to 0. In the denominator, we have 1 minus 1 times 1, and so we have 1 minus 1, which is also equal to 0. So it's an indeterminate form. We apply L'Hopital's rule. Remember, L'Hopital's rule is a method to deal with these indeterminate systems. So we can think about the effectiveness as a function of the capacity ratio divided by a different function of the capacity ratio. We see that as the capacity ratio goes to 1, that this is 0 over 0. So to evaluate it, we do f prime of RC at RC is equal to 1 divided by G prime of RC at RC is equal to 1. And what we get is NTU over 1 plus NTU. So if you go through the steps, you'd find that this is correct, and I encourage you to go through those steps, but it's not necessary for us to go through the details right now. For the counterflow heat exchanger, there are some other interesting things that occur, both in terms of the way that the curves, the temperature curves, behave, and in particular for the case of this balanced heat exchanger formulation. So for the balanced heat exchanger formulation, the thing that you want to see is that the counterflow heat exchanger problem. So let's just take a look at this in a little bit more detail. And maybe it's worthwhile thinking about this for a more general case first. So in the most general sense, where we have a flow between x is equal to 0 and x is equal to L, we have different possibilities for what the temperature distributions might look like for the counterflow heat exchanger. And I'm just going to sort of sketch sort of a crude case here where we have these two curves. And so in the curves that I'm sketching here, and I'm just going to talk you through this a little bit, we have a hot stream that's going from left to right and a cold stream that's going from right to left. And if one were formulating this problem, the way that you would formulate this problem in terms of the hot stream is you would say that CH dTH dx is equal to minus let's use U minus UP TH minus TC. So this is a case where the temperature gradient dTH dx is negative. Now, on the other hand, if you look at the cold stream problem, you'd say Cc dTc dx is equal to, and so this is an important issue here. And so with increasing x, we have a negative value of the temperature, and so we have to recognize that this is actually sort of an odd problem. We have a minus UP TH minus TC. So TH minus TC is a positive value, and the TC dx is negative. The way that I think about this is that the mass flow rate is actually negative. The velocity is negative for the cold flow. It's positive for the hot flow. You have to remember that CH or CI is, while we say it's m dot times little c, you can think about that also as rho times a velocity times an area times this, oops, let's just make this CH here, times this heat capacity. So the velocity matters, and the sense of the velocity matters in terms of the evaluation of this problem. So this is a really important issue in terms of how to think about these problems. In this particular case that I just described, what happens is that when we subtract off the differences between TH and TC, for example, where the case is that CH is equal to TC, you see that if these are equivalent, then dTH minus TC dx is equal to 0. That is, that the temperature difference is a constant. So that's a very important issue in terms of this. The way that I guess when I set this initial problem up is a little bit different from what I set up in this case down here. I actually had that both TH and TC were increasing functions of x. So in this case, what I have is a hot stream. So this is a hot fluid stream coming in, and a cold fluid stream that is coming from the right, and a cold fluid stream coming in from the left. So this is a bit different from what I have here. So let's just keep going, and I'll show you what exactly I mean by that. All right, before going into that, the essential part that I wanted to show is that for this RC equal to 1 in this counterflow system, the temperature difference is a constant. TH minus TC is a constant. If TH minus TC is constant, then dt dx is a straight line. We find that we have straight lines because, again, if this is a constant, then this is what we have. So let's just talk about the more general case that I was alluding to. So the more general case that I was alluding to is really that we have to pay attention to the sign issues here. So in the we'll continue with this counterflow case that I was talking about. So for the counterflow problem, the math gives us an indication of what the issues are. So if we have, sketching it here, if we have a hot stream coming in, TH in, and leaving at some TH out, and a cold stream TC in with some TC out. What we'd like to do is we'd like to understand what shape this curve looks. And so the issue becomes, does the curve look like this? Or do the curves look like this? Or do the curves look like that? And the math of the problem will allow us to understand what the shapes of these curves are. So first thing to do is we understand that dth dx is equal to so we have for sure, we know that this is a positive temperature gradient. So if it's a positive temperature gradient and th minus tc is a positive number, then this has to be UP over CH TH minus TC. And for the cold stream, it's dTC dx is UP over CC TH minus TC. So this, we know that they're both dTH dx and dTC dx are positive. As we go from small values of x to large values of x, we know that the temperature is increasing for both streams. The next issue is that if we look at the second derivatives, and seems a little strange, but it's important. So as we look at the second derivatives of these values, so let's look at d squared t dx squared. So that's equal to UP over CH times dTH. So we're just taking another derivative of each of these quantities. And this is what we get. We get dTH dx minus dTC dx, okay? All right, so the question is, what is the second derivative of this? Well, we know that the first derivative here, dTH dx, is equal to a positive number. And we have here that the dTC dx is also equal to a positive number. And in fact, dTC dx and dTH dx, we know in terms of their respective values from the first problem. So dTH dx is UP over CH TH minus TC minus, so this is the expression for dTH dx, and dTC dx is UP over CC TH minus TC, close. So this is again dTC dx. And so the issue really is a question of which one of these is larger. So if CH is less than CC, and I think that you can see this here, so, but if you can't, let me just expand on this a little bit. So dTH dx squared is equal to UP squared 1 over CH minus 1 over CC TH minus TC, okay? So if CH is less than CC, then this is a positive number. So the right-hand side is positive. So RHS is greater than 0 if CH is equal to CC, then the right-hand side is equal to 0. And if CH is greater than CC, then the right-hand side is less than 0. Okay, now there's an old rule about the second derivative in terms of showing the convexity or concavity of a curve, and the simple way to remember is if the second derivative is positive, you have a curve that looks like that. If the right-hand side is negative, you have a curve that looks like this. What does that mean? It means that if the right-hand side is positive, that is, if CH is less than CC and RHS is greater than 0, then we have a curve like this, and it means that our temperature distribution looks like this for our hot stream. If, on the other hand, CH had been greater than CC and the right-hand side was less than 0, it would mean that our temperature distribution would have looked like this. So these are important ways of understanding what is going on in these problems. We have all the tools available to us to understand how these temperatures behave. We can do the same thing with the cold stream temperature distribution, and we can in fact do the same thing with the co-flow type problem. And in the co-flow problem, for example, we would see that our distributions are always second derivative for the hot stream would be positive, second derivative for the cold stream would be negative, and we always have the sort of the form that we would naturally understand to occur for that type of problem. And of course, in this case, if the hot stream and cold stream are balanced and the right-hand side is equal to 0, it says that the second derivative is equal to 0, and the first derivative is a constant, which is what we knew it to be, and that the temperature distribution itself is linear. So everything that we understood about this problem to be true is evident just by using a little bit of math to explain what we saw.